Alrighty, so welcome to class, Robbie. And Ted. So I've had a couple questions on the last project, the Nbody simulation, that I think bear answering for everybody. So let me looky here. Okay. So the question is, for the half ring, we have to send positions and then this complementary force array. And both of these are arrays of vectors, or vectors of arrays, however you wish to do it. Which means that when you're doing sends and receives from one processor to another, okay, basically the question is that the send for the positions and the send for the forces look exactly the same. And then the receives for the positions and the receives for the forces also, they look exactly the same. Okay, you're sending the exact same amount of data, and so the question is, how does it differentiate between the two? How do we make sure that the positions are going to the positions and the forces are going to the forces? And so the answer is, the MPI standard says that if two processors are communicating and there's multiple messages being passed between them, then they will arrive in the same order that they are sent. So if you send the positions first and the forces second, then they will be received in that same order. Okay, so you can rely on that. However, there is a more explicit way, and that is using the one thing we have never used. Hey, we got someone else. We can use the MPI tag to differentiate between the two. Okay, so, and the tag is just an integer. Okay, so it'd probably be best if you either made an enumeration, call it tag, and just say that the first one is positions and the next one is forces. Okay, so you can make your enumeration like that. And then for the tag parameter, instead of just setting that to 0 like we've been doing, you just use position or force. Okay, now you could use defines, but those are generally, you could say define capital position as 1 and define capital force as 2. You could do that. Defines are kind of frowned upon in C++, but they are available to you. Enumerations tend to be a little more C++-y. So there is that. And then there was another question on, so we have visiting positions, as I've called them. Okay, so if we have a big array of our visiting positions, how do we receive new positions and send old positions? Because then we have basically a data race condition. We have the receives working off of this and the sends working off of this. So if the send is copying data and it gets halfway through, when the receive starts, if the receive is getting new information while the send is trying to send the old information, we could get garbage, or this guy over here could actually get half of the values from over here. And so there's two ways you can do that. you can basically, the simplest way is to just copy the data to a new array, and this will be your send buffer. So you send from here and you receive into here. Okay, so that's the simplest way to do it. And there is a different way to do it. So first off, I wanted to note this routine here. MPI send receive. I've told a few of you about it, but I thought I'd just let everybody know. I think I did mention it in class, but I sort of skipped over it. This is a combination send receive function. It sends data to somewhere and receives it from somewhere else. It's guaranteed to not deadlock. And so you notice it has a send buffer, the amount we're sending, the type we're sending, where it's going, the tag for that. And then at the same time, we also have a receive buffer, which is and how much data we're receiving.
So what's the point of having a tag if it's not going to deadlock? Like, what's the point of having a tag if you're sending and receiving all in one?
The tag just is a kind of a note. This is this kind of message. It's like you put a sticky note on your envelope and say, this is positions, this is forces. Tags actually come in handy in more complex applications than what we're doing.
Okay. I guess it just seems redundant to me in this function that if it's already, because you mentioned that we're using tags to avoid sending it to the wrong place,
Right. So in this case, the tags come in more handy when we're dealing with asynchronous communication. Because then we can know for certain that we're getting exactly what we want. So anyway, and then where we're receiving from. So this is basically made for ring shift applications. Because they are so common, they gave us a nice little combo function here. And then there is this one. I actually didn't know this one existed until this morning. The MPI send receive underscore replace. So this has one buffer, the size of that buffer, the type, where we're sending it to, the sending tag, where we are receiving from, the receiving tag, and then of course the communicator and the status. And so this actually, notice we only have one buffer, and it will send what's in this data or in this buffer and then replace it with what it receives. And I'm assuming it does so without data raises. Okay. And probably actually what it does internally is just makes a copy. So that's probably what it does. It's what you would have done manually, but there's a nice little convenience function for you.
So if it's internally doing the same thing, which is more efficient in terms of just parallelization?
It's more efficient for you because there's less for you to do. So there is that thing to take note of. And it is also, it may be that they don't do that. Maybe they have a special algorithm that takes care of it. I don't know. So as far as efficiency, the only efficiency I see is it's less effort on your part. Okay, and you can assume that they are doing things correctly. So anyway, I thought I'd point that out, that these things exist and they're useful. They are blocking, so this is synchronous communication. It's not asynchronous. It will stop and wait for everything to finish. So anyway, I hope that answers everybody's questions on that and gives you a little head start on how to do that. So now I've had a request to talk about Fortran. Now, I know all of us are using C++, and I will get to advanced C++, but I have a student that wants to do the last project in Fortran. So I'm going to talk a little bit, actually a lot about Fortran today. And I'm going to give you some examples, because personally I love Fortran. I think it's great. C++, you have to get a master's degree in it to actually be able to use it. And I feel like Fortran, you don't. So, all right, first off, Fortran has a reputation amongst programmers, maybe not engineers, but real actual programmer computer science people. It's like the laughing stock of the computer programming language world. Has a reputation as being cryptic, unusable, archaic, old-fashioned, all that fun stuff. What they're talking about is the old Fortran. This is Fortran 6677. Okay, notice the all caps. And let me just say, it is awful. Robbie can attest to this. He's trying to use a function that's written in it. LePac is written in it, and so that can be a pain in the butt to get working correctly. And yes, my dad did use it in college and did not like it, and I don't blame him. However, in 1990, we had Fortran 90. Notice we're now not all caps anymore. It used to be all caps because it was an acronym. It stood for Formula Translator. You're supposed to translate math formulas. So Fortran was made to do math, and since we do math, it's pretty handy.
So it's no longer an acronym?
It's no longer an acronym. It has been promoted. Just like Google is now a verb, right? Hankies are Kleenexes now, you know. Kleenex is a brand name. Q-tips is a brand name. We got called them all Q-tips. So anyway, completely changed everything. There was a small update in 1995. In 2003, object-oriented programming was added. 2008, we had submodules and parallel programming. And note that this is not your father's Fortran anymore. It's completely different. And you don't need to write in all friggin' caps anymore, which is really nice, because all caps is hard to read. And I don't care who you are, all caps is hard to read. All right, you should get a nice text editor with syntax highlighting, and it takes care of that for you. However, you should note that Fortran is case insensitive, so this can lead to more easily lead to naming clashes. I think this is a mistake on their part, but that's the way it is. So, I mean, you can write in girly caps lowercase if you wanted to. That's even harder to read. So, all right. First off, some information about Fortran. Fortran is not as supported as other languages. It doesn't have a large user base, and it can be hard to find good information. So first off, there is fortranwiki.org. They're trying to be the authority on Fortran. They're not succeeding all that great, but you know, it's there. The best place to get information is from the Usenet group. I don't know why I didn't jump to it, but okay. And there's a lot of old timers on here who know like everything. And there's a lot of, you can ask questions there and they'll get back to you shortly. It's an email list. Stack Overflow, there's probably like 20 Fortran programmers that frequent that, and they're all really smart and they all answer questions really well. GitHub has a lot of examples about using modern Fortran, a lot of very useful codes and libraries on there. All right, so this is very, very important. I don't know if it, okay. So since it doesn't have as large of a user base, the compilers are not updated as fast as like C++ compilers are. And so it's important to know what has which compilers support what features. I mean, you always need to know this, but in general, the Fortran 2003 status has a list of everything Fortran 2003 added, has a list of compilers here, and what they support. Generally, Cray, PGI, and Intel have full support. The more common G Fortran does not support some things, and partially supports some things. So it's important to know what you can and can't do, depending on your compiler. However, most of 2003 is implemented in G Fortran. 2008 here has a lot more red. Okay, even Intel, PGI, Cray is the only one that I think is fully supported. Yeah, but we're not using Cray computers, so, there goes that idea. So anyway, a lot of what I'm going to talk about, you probably need to make sure that it all actually works the way it should before you try it. Anyway, another useful little website is this one. Mistakes in Fortran 90 programs that might surprise you. Has a short list, but of things that are pretty common and things that you could mess up. So there's that. So now to get started. First off, rule number 1, when you're dealing with Fortran, always, 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 always put implicit none at the top of your program, at the top of your module, in your subroutines. Most compilers have a little switch that you can just switch it on, but that's not something you want to rely on. Use the standard and use implicit none. And this is because old Fortran, you didn't have to declare types, you didn't have to declare names, you could just throw stuff in there willy-nilly, and it caused a lot of headaches. So this is there to prevent you from having super large headaches.
That's nice.
Yeah. So data types. Fortran data types are not very standardized until fairly recently. You'll see this a lot. This real *8. Why is my thingy not? There we go. Okay. Yeah, so let's go back. Real *8, not part of the Fortran standard. Okay, those are compiler extensions, and they're not portable between compilers. So, the 2000, I don't remember, one of the later standards defined this, the ISO Fortran environment, and it defines very specific data types. Okay, and this is what I would default to with anything that you write new, and I'll show you an example of that in a bit. And then there's the selected real kind. This is the Fortran 90 option, which was kind of cool because it would just automatically give you the right type. You tell it, I want to make sure I have 17 decimal places and I can get to plus or minus 10 to the negative 300. And you tell it that, and it'll spit out the correct type for you to use. But we'll get to that. I'll show you an example of both of those. So, modules. All functions should be placed in a module. Okay, that's rule number 1. You should never have a standalone subroutine anymore. If you go on the internet, you'll find people's personal collections of subroutines that they wrote way back when. And so if I need one of those, I will take it and put it in a module. So that way I don't screw a lot of things up. And Fortran is not the only one to have this module concept. In C and C++, we have the C file and the header file, the H file. And the header file defines what a function should look like. The C file defines what the function does. The module does both. Okay? So when you compile a Fortran file, which has a module in it, and you can actually define multiple modules in a single file, it will generate a .mod file. Okay, and this .mod file is basically the header file. It's writing the header file for you based off of the implementation file. And so, unfortunately, .mod files are compiler specific. The standard does not say what they should look like. Oftentimes they break from version to version. And so you can't use an old version with a new compiler. So you have to recompile it to get the new .mod file, which is a little annoying, but there you have it. Everything in a module can see everything else in that module. You can declare private and public module members. You can only import specific things. Unfortunately, you also have to compile modules in the correct order, and that's kind of a pain in the butt. And recursive modules is not possible. So if module A needed module B and B needed A, you can't do that. It has to be a linear relationship. If you wanted that, now we can use submodules, which I'll get to, but you basically have to stick everything in the same module. So let me just show you an example of these things. Oh, that's the wrong password. Dang it. Okay. So, for those of you who took my fluids class and did that first project with the vortices all flying around and you had to do the path lines and stuff, this is how I did it. So I had a module, called it vortex_m, for M standing for module. You can see here I'm using the precision module, and I can actually open that up. Okay, we'll type PR, there we go. And here's my precision module. And so here I'm using the intrinsic ISO Fortran environment module, and I'm importing, it defines a lot of things, but I'm only going to import the real 64 type. And this is a real or floating point type that has 64 bits. So ISO Fortran environment, here's a definition, defines a lot of things. So it defines int 8, 16, 32, 64. It defines real 32, real 64, and real 128. And a lot of other things that we really don't care about most of the time. But those are the big things. I don't know if this list is complete or not. But the big thing is those types, because then we know exactly what we're getting. However, there is another way to do it, and I will show you. And that's using the selected real kind. So I could say and this is a function which the compiler can actually run at compile time. And so we tell it we want to have at least 14 decimal places and that's the precision. 14 decimal places, and we can define also a range of plus or minus 10 to the minus 7. 10 to the plus or minus 70. Okay. At which point it spits out a type personally customized for your hardware that will work, that will give you exactly what you want, which is kind of cool. But however, I personally prefer this real 64, specifying exactly what I need. I need 64 bits. And if your hardware doesn't support that, which it really should nowadays, it will give you an error and tell you that doesn't work. So Really? There we go. Okay. So here I'm using that. And what that does is it actually imports everything. And everything in a module is, by default, is public. So anyway, here you can see I'm using that DP parameter as a kind for my real type here. So this is a double precision parameter, and I'm declaring that to be pi, and I'm doing that using the arctangent of, or sorry, the arccosine function. Anyway, so that's kind of a basic look at modules and types. Okay, now we come to allocatable arrays. All right, so allocatable arrays. They are dynamic arrays. They have a rank, which means they can be one-dimensional, two-dimensional, three-dimensional, four. I think now the standard says you can go up to 15 dimensions. So those are some really big arrays. They have a rank, a dimension, so 2 in the x direction and 4 in the y direction. And then a lower bound, which is really clever. You can actually specify that this array starts at 0 or starts at -1. And so you can actually index using -1. However, just make sure you note Fortran is column major and 1 based. So first element is not addressed using 0, it's addressed using 1. Unless, of course, you change the lower bound. And this is really important. You have to beware the automatic reallocation. So if I have an array, oh bother, like an allocatable array, okay, and I am going to allocate him to be size 10, and then let's say I have another one, array B, to be size 5, and then I say A equals B. Okay. By default, what this will do is it will say, oh, A and B are not the same size. So it will deallocate A and reallocate it to be of size 5, at which point it then copies the values from B into A. All right, I didn't know this existed, and I found it out the hard way, that this existed. So there's a couple ways you can deal with this. Compilers do have flags that will let you turn that feature off, or you can prevent it by using the slice notation here, like that. And so the slice notation will, you can't reallocate a slice. You can reallocate an array. So just so you know, there's that. Every compiler has options to do bounds checking because your array knows how big it is. You don't have that in C or C++. And so you can turn that on and it will tell you if you've made a mistake rather than having to track down stupid memory bugs somewhere. So always turn that on. Find that flag for your compiler and turn it on. If you pass an allocatable array to functions, okay, the way you do this, you have some function, and he gets an array, and you say this is a real of dimension this, okay. If you do that, then the lower bound does not get passed in. I don't really know why exactly, but it doesn't. I found that one out the hard way too. All right, and here comes the coolest thing about Fortran is you can do array slices. So you can say A2, assuming we had a 2D array, this would take the entire first column, or sorry, second column of A. And you can do math with it. You can say times 2, and you can plug that into B. And if B is the wrong size, B will get reallocated to the correct size of this column. You can do from 1 to 3 in steps of 2. Okay, array slices are awesome. However, if you are passing an array slice into a function and it's not contiguous, the compiler may, or it may not, create a temporary copy. And again, compilers have flags so you can turn it on, turn it off, throw a warning if this is going to happen, because temporary copies will really slow down your code, though, because it makes a temporary array, packs everything into the array, and then passes that into the function. When the function exits, it takes the values, unpacks them back to where they came from. Whole array statements. I can do A equals B plus C, and that does the whole array. No loops necessary. So that's convenient. And then there's the where statement, which is really cool. And I'm going to show you an example of that. So it's actually in here. So I have here this function here, I'm passing in x, y, u, and v, which are two-dimensional arrays here. Okay, and then I'm creating these allocatable arrays. And this may or may not be necessary, but I'm allocating them explicitly to the size that I need. And then I'm doing a whole array statement here. So I'm setting r equal to the distance from the vortex center. Okay, and since these are Rankine vortices, I need to have two different basically definitions of the r. And so I'm saying wherever r is greater than a, and so a is set right here, and that's the distance where we switch from the linear Rankine vortex to the irrotational Rankine vortex, or sorry, the solid body rotation to the irrotational portion. So wherever it's greater than a, I'm going to make that an irrotational vortex, and wherever it's less than a, it becomes a rotational vortex. And so I can do this to this entire array in this little bitty statement. No loops necessary. So that is super handy and super cool. And there really is no way to duplicate it in C or C++. I've thought about it a lot. All right. Array intrinsics. Fortran comes with a bunch of array manipulation functions, which are super handy. All says, is everything in this array true? Is any of them true? How many of them fit this criterion? What's the maximum value, the minimum value? What's the location of that maximum value over here? A circular shift, an end-off shift. You can reshape them, you can unpack them, you can pack them, you can spread them, you can merge them. You can find out what the upper bound and the lower bound, the shape, the size, whether it's been allocated or not. Do a sum or a product of the array. Arrays are what they call first-class objects in Fortran. They are a thing, whereas in C and C++, they are not a thing. They are a byproduct of allocating memory. All right, so functions, subroutines. Data is passed by reference. Unless you specify, it should be passed by value. Intent. This is really important. When you have a function, and I know it's verbose and it's difficult to type all the time, but there you have it. You have to specify the type of A and B. That's what the implicit none statement is going to tell you. And so we have to say that A is a real, but then we can also specify the intent, and you should always specify the intent. if we specify the intent for A to be in basically is like a const parameter in C or C++, okay? It's saying this should not change inside of this function. It's only getting passed in. If we did intent out says this variable will be modified, okay? However, this is dangerous because, first off, it causes allocatable arrays to be deallocated. And what I mean by that is not if it's an allocatable array, but if the function knows that it's an allocatable array. For instance, you can actually declare that your array is allocatable, like that, okay? In which case, inside the function, you can now allocate it or deallocate it. If you try to pass an array that is not an allocatable array, it will yell at you and prevent you from doing that. So generally, you don't want this, okay? But in certain situations, you do. So also, the variables lose whatever value they had when they get passed in, if they have an intent out. And it applies to all members of a derived data type. So if you have allocatable arrays inside a derived data type, those will be deallocated. So that's bad juju. Don't do that. And I've, of course, found that one out the hard way too. Functions have optional arguments, and those are pretty cool because you can specify a lot of things, and then you don't have to necessarily pass them in. Named arguments, you can actually, when you call the function, you can say A equals my array and B equals, I don't know, death. Okay, and you can actually switch the orders on these because you've given them a name. So that's kind of cool. Automatic arrays, if you pass in, say, an integer into your function, and then you can make an array later on inside your function of size A. This is called an automatic array. It automatically gets allocated inside the function to that size, and then it gets deallocated when the function is over. You can rename the return value using the result clause. So the return value of a function is always the name of the function. But if you don't want that, you can add the result clause, and then you can rename it and say, oh, I want to return the variable O instead of the variable my function. By default, Fortran functions are not recursive. So there's a recursive clause that you can put on the function name. Pure functions are really useful, or it's really good to understand. A pure function has no side effects, as they call it. Now, what that means is, I'm going to have to erase all this stuff. Nope, that's what I wanted. Okay, so a pure function, it's something you put on the function name itself. Has no side effects, which means it does not modify anything that gets passed into it. It does not do input-output. It does not do anything crazy or unexpected. So basically, it gets values, it returns values. It's like the square root function. It gets a value, it returns a value. That's all it does. And this is important for the compiler because the compiler, if it knows a function is pure, can then do further optimizations on that function. Elemental functions. So this is another specifier that you can put. Now elemental functions are really interesting because you can actually, you declare it as if you're receiving one value, but then it can operate across entire arrays of values. And so you can save yourself a lot of loop writing if you can write elemental functions. Internal functions, these are cool. Inside your function, you can have a contain statement. And below the contain statement, you can have another function. And this function is internal to that function. Only this function knows that that one exists. But if you find that you're writing small pieces of code over and over again, you can actually take that out, put it in a small little function, and simplify your code in the big function, in the parent. And everything I'm talking about here with functions also applies to subroutines. So, interfaces allow you to overload functions. So normally, not normally, but in C and C++, not C. C doesn't let you overload. But in C++, you can have a bunch of functions of all the same name. And the only thing that's different is this one takes numbers and this one takes characters. Okay? And the compiler automatically figures out how to go about which one to call based on what you're passing in. In Fortran, you can sort of do the same thing, but you have to give them different names. So this one we're going to call myfuncNumber, and this one we're going to call myfuncC, and then you have to declare an interface. And I'm not showing you all the particulars about this. I'm not trying to teach Fortran. I'm just kind of giving a demonstration. And we call this myfunction, and then we say basically that myfuncNumber and myfuncC can both be accessed using the same name of myfunc. And you can also use interfaces to pass functions to other functions, so that's useful. Pointers. Fortran finally added pointers. However, you don't really want to use them most of the time. Usually you can get away with using allocatable. And I forgot to mention the most important thing of using allocatable arrays, and that is because they are automatically deallocated when they die. Okay, so you don't have to worry about the memory management. And that's the important aspect of using allocatable arrays. Pointers, however, are not automatically deallocated. And so if you want to point to something with your pointer, let's say A is a pointer, you have to point to it, literally point to it with the association operator, okay? By default, if you use the pointer now in a math expression, it uses this value. It's dereferenced by default. If you want it to act like a pointer, you have to be pointing to something. Pointers can also point to entire arrays. And so we can point to the array B and then now treat it like an array. However, you have to name something as a target before you're allowed to point to it. So that's important. You can find out if the pointer has been associated using this function. You can nullify it using this function, or you can set it to null when it's first initialized using the null function. So if we did pointer A, and then we point it at null like this, later on in the code we can nullify it with this function, like so. Arrays of pointers are a different thing. So a pointer with the array syntax is pointing to an array. It is not an array of pointers. However, we can do it with derived data types. And again, let me just say, most uses of pointers can be replaced with allocatable scalars. Use this instead if you can, because it's much safer. It handles the memory management for you, and it prevents aliasing. So, just so you know. Derived data types. In their basic form, these serve the same purpose as a C struct. You can access members using the % operator. You can use them to build an array of pointers, and you can assign default values to them. So here's an example of this. So the simplest example I have here is this vortex type. So I say type, I give it a name. Everything inside of here, these are the variables of the struct, if you want to call it, and then we can end the type. So there's that.
So what is in there? What does the procedure mean?
I'm getting to that.
Oh, okay.
In 2003, they allowed you to start doing object-oriented programming.
So it's a class, not just.
It turns it into a class. Okay, we say this type now contains certain functions. Okay, it contains a procedure called update position and another procedure called add vortex. And so here in the module now, we have this contains, we now contain the subroutine. Okay, so this is what it's pointing to. And what's really important about this is now these two functions, normally if you were just using a function, you could say type. Okay, but type refers to the basic structure usage, not the class usage. And so if you want to, there we go. Wow, I have caps lock on. Okay. And so these functions you have to pass a class, not a type. Okay, that screwed me up for a while when I was learning this. And by default, you always have to pass in the very first argument is the object itself, is the class itself. And so you can call it whatever you want, but I always call it self. It's very similar to the this pointer or the self in C++ or self in Python. I prefer the name self. I think it makes more sense than this. Like this what? Anyway, so it's referring to myself is what that is. Anyway, so again, you can associate the module functions with the derived data types. By default, you pass in yourself into that function. However, it is possible if you use the no pass here to get around that. You don't have to pass yourself to the function, which is really nice. You can make abstract classes. If you make it abstract and you can now basically says you can't actually allocate this class. You can only allocate its inherited, its children, its polymorphic children. Using the and then you can say this function definition is deferred, but it will be called fk1. And then you use the interface to tell it what that function is going to look like. Again, I'm just going through this quickly. I'm not actually trying to teach this, but give you an idea so when you look this stuff up, you can understand what you're doing. All right, you can declare private and public members. However, this is not the same as C++. And this screwed me up too, is that a private member is private to the module. And so you can't actually access it in the children anymore if you have the children in a separate module. So I find in Fortran it's generally easier to just leave everything public and just, either use a naming convention to like Python does, because in Python everything is public. And they say if it starts with an underscore, it's a private variable or a private function and you shouldn't be using it. However, you can't start with underscores in Fortran, so I end with the underscore instead. Abstract types, allocating polymorphic types with typed allocation. I don't actually have an example of this because I didn't learn about this until much after I stopped using Fortran. But in order to allocate polymorphic types, if we have a class and it has to be allocatable or a pointer, one of the two, and we can allocate A like so. So rather than using the type, or we'll call this P for parent, rather than using it becoming a P type, you can actually say this needs to be a child type here. You can overload the assignment operator. You can overload plus and minus and multiply and divide. You can overload any of the default math functions, square roots, cosines, sines, all that fun stuff. You can actually invent new operators using the dot syntax. And so this isn't really necessary, but if you wanted to implement a dot product between two of your vector classes, you can actually invent one called dot, and then you can say A equals C dot B, like so. It's a little verbose, but it's kind of cool that you can invent new operators to do what you want. I've thought about making a super cool like string library where you could like have a bunch of new dot things like regular expressions and stuff like that. So it's kind of cool. In 2008, they added basically destructors. Oh, you can also do constructors. So that's nice. Anyway, so yeah, destructors, they finally added those, but they're not very well supported. You can make special writing functions to do input and output, arrays of objects, and then there's the unlimited polymorphism. This is their version of the void pointer in C and C++. Class star. This can point to anything. It can be allocated to anything. And then in order to actually use it, you have to have these select type constructs, which are very similar to a select case kind of thing. And then sourced allocation, you can actually allocate an unlimited polymorphic pointer. I know, right? And so we can say A, and then we say source equals B, and it actually allocates it to be the same type as B. So there's that. Strings. Fortran strings are very, very different from C strings. And this can really get confusing. But they're sort of like arrays, but not really. Because if you have a character variable, you can actually give it a length. Okay? At which point you can treat it a lot like an array after that. And so this string is always of size 10. Okay? And if you read in a string that's of size that's only 2 characters long, it puts those up front, and then we have a bunch of spaces at the end. They finally added where you can have an allocatable string. So it's not like a C string, which has some text and then ends with the funny little null character. And that's how you know where the end is. The end of a Fortran string is however long it is. It has a bunch of functions that you can use to work with them. This so adjust left, adjust right will get rid of any empty space inside there. Index will tell you the index of a particular substring. Length trim is the actual length if you trim the space off of both ends. Trim actually trims it, which is nice. Scan will find substrings for you. Length tells you the length of the string, which is this length, it's the length of the string, not the length of the characters inside the string. If you want that, you have to use length trim. Interacting with the operating system, you can get command line arguments. You can execute programs on the command line. You can get environment variables. There is the inquire function, which you can use to check for files and check for permissions and fun stuff like that. All right, file I/O. This is kind of a big thing. Fortran files are generally record-based. And honestly, I don't really know what that means exactly, but it takes your file and it puts these records in it. And this causes huge problems when you're trying to pass files between programs or between operating systems. And so, because it's record-based, while the rest of the world is stream-based, which basically means our file is a big thingy and we're just going to write to it. Okay, instead of chunking it up into these records. So, modern Fortran, this is the open function and everything you can possibly specify for the open function. All right, but I'm going to point out the big things. First off, you have to specify a unit. Now in Fortran, all the files have an integer handle, as it's called. And it's not your job to know what is a good integer. So rather than that, they now have what's called new unit. And so you just do new unit, and you give it an integer variable, a, okay. I like to use IOU for IO unit. And then you can use that variable later on when you want to write to that file. And it goes and finds an appropriate integer value for you. All right. Anyway, access has 3 different options. Just use stream, okay? It's going to be easier in the end, I promise. You will have to manually add new lines, so we can get new lines from either the ISO-C binding module or the new line function, okay? It allows you to use asynchronous file I/O, which is kind of nice. And then there's a lot of other options that I'm not really going to worry about. All right. Format specifiers, internal files. How do we turn numbers into strings and vice versa? With read and write. You can actually treat strings as files, which is really cool. So your normal read, you have 2 statements. The first is the file. And so if you want to read from a string into a number, you can say read from my string, and then you specify the format. A star gives you the default format into our number. And so we have our number. Now if we wanted to go the other way, we want to write to our string, the default format, and we put our number. Okay, and we treat it just as if it were a file. All right, so the format, these stars here. Star is kind of what you generally want to use, but you can specify the format of what you want. And these are very cryptic, but very powerful. You can put them in a string and use them. So we can have our format string, and we put in our format here. And then instead of a star, we use FOR for our format string.
I don't mean to cut you off, but it's 11:40.
Oh, is it? Oh, gosh. Okay, well, there's a few other things that I wasn't really going to cover all that much, but the C preprocessor, you can do that. It's not standard Fortran, but you'll see it in a lot of old Fortran files. Interfacing with functions written in C. Learn this if you're going to be doing this, okay? This is the best way to do it. Associates, blocks, co-arrays, submodules, parameterized data types. I wasn't going to cover those because they're not very well supported. So anyway, there you go. We're done. Sorry for keeping you over. Lost track of time. Anyway, keep asking me questions and emailing me about the projects. So